Imagine a hospital trying to predict if a patient is at risk for heart disease. To build a system that can help, they start with two measurements: cholesterol and blood pressure. This chart tracks those two variables, with the horizontal axis for cholesterol and the vertical axis for blood pressure. Every patient lands somewhere on this board based on their numbers. When we plot the data from past patients, we see a pattern. We'll mark those who developed heart disease with red dots and those who stayed healthy with blue squares. By providing these labeled examples, we are essentially showing the computer the correct answers from the past. This teaches the system how to recognize the difference between a high-risk profile and a healthy one. The computer's job is to find a single dividing line that sits between these two groups. Once that line is drawn, any new patient can be instantly classified just by checking which side of the boundary they land on. The problem is that there are thousands of ways to draw a line that technically separates these clusters. The goal is to figure out which of those lines creates the safest, most reliable gap for future patients. This is the specialty of the support vector machine. This algorithm solves the problem by searching for the widest possible street that can fit between the two groups. To find it, the computer expands that central boundary line outward in both directions, carving out a wide path. The street stops growing the exact moment its outer edges physically bump into the closest data points from either side. Those edge-touching dots are the support vectors. They act like the pillars that hold the entire street in its specific place. One of the most powerful features of this approach is that the computer ignores every other point that is safely behind the lines. The final boundary is determined entirely by those few tricky points right at the edge of the street. As this diagram shows, moving patients already deep in their zones has no effect on the street. Their positions don't change the decision. However, if an edge-touching support vector moves, the entire street shifts to maintain that maximum gap. This means the system can process millions of data points while only needing to track the specific few that define the edge, allowing it to find clear boundaries in massive amounts of noise. In some cases, the data is even more complex. Imagine a dataset where the successful points are in a perfect circle, completely surrounded by failures. You see this in things like drug dosages. A dose that is too small fails, and a dose that is too large fails, but the middle range works perfectly. If you are looking at this from a flat perspective, it is impossible to draw a straight street that separates the center from the outer ring without hitting the data. The computer solves this by performing a dimensional shift. It uses a mathematical formula to lift these points off the flat page and view them from a new perspective. As the points lift, the inner green dots drop down, while the outer red ring rises up. Suddenly, the data forms the shape of a 3D bowl. From this angle, the two groups aren't tangled anymore. They are vertically separated. Now, the algorithm can easily slide a flat, rigid sheet of glass straight through the empty space between the upper and lower groups. If we project this solution back to the flat page by looking straight down from above, that flat sheet of glass appears as a perfectly drawn circle that isolates the center group. This dimensional math is what allows computers to perform complex tasks, like filtering spam from your email, identifying objects in photos, and mapping human protein structures. Whether the solution is a simple street or a complex 3D shift, these machines find the safest boundaries to bring order to our data.